I'm still paying you. I got the hard ass beats like the crack of the tech. I'm still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. I'm still paying you. I'ma make y'all pay for the dues.
Let's get started. A lot to cover. Round of applause for DJ Cash. Again, thank you for keeping everything fresh. All right, so like I said, a lot to cover today. Plus, we have the guest speaker, so I'm trying to jump right into it and try to get as much as we can, cover as much as we can today. All right, so last class was the last lecture we did, or the previous lecture. We sort of wrapped up our discussion on what the storage layer of the database system looks like. Right down on disk, we already talked about buffer pools and how to bring those into memory. So now we're going to start going up the stack. You remember this diagram from the beginning of the semester, where we're now going to start talking about how we're going to build the support infrastructure in a database system to start executing queries. So we're going to be sort of this middle layer here, what I call access methods. It's basically what the API we're going to expose to the operator execution, the execution end up above to get access to the data that we want. So today and for the next week as well, we're going to actually talk about data structures. We're going to build on top of our buffer pool manager pages now that we can use to store data for a variety of reasons. So today's class will be about hash tables, so unordered data structures, and then all next week will be about trees or ordered data structures. So again, we're going to talk about the background about why we want to do this, why we need our own data structures, why you don't want to use STL vector for the stuff that we want to do. But then we'll quickly talk about what hash functions look like. Then we'll talk about two approaches to do hash tables. The first will be static hashing schemes, where you assume the size of the hash table is fixed. And then there'll be dynamic hashing schemes, will be a data structure that can grow and shrink depending on the number of keys that you're going to put in it. And in a database system, you're typically going to need both of these, right? Because as we'll see in a second, we're going to use these data structures for a bunch of things. And then we'll finish off with a guest lecture from the Yugabyte co-founder. Okay. So these data structures we're going to build here are going to be used, again, all throughout the database system for a variety of things. Obviously, we could use them for table indexes. That's probably what you're most familiar with at this point. Like, how do I take a primary key or a secondary key, do a lookup to then find the record ID that's going to be on some table page. But we're also going to use them for internal things like the metadata, like the catalog of the database. We talked about the page directory. It's this hash table structure we use to look up to find the location of pages within files. We can also use this for the core data storage itself. We saw this before when we talked about index organized storage, where we said that instead of having these unordered heap pages for our tuples, we're actually going to store the tuples in the leaf nodes of a tree data structure, typically a B+ tree. And then another one that we're going to see as well, but we'll see mostly when we talk about query execution, we can use these data structures for temporary data storage. So when we do a hash join, when we want to join two tables, if we're doing a hash join, we're going to build a hash table, one of the hash tables we'll talk about today, populate it, do the join, and then immediately throw it away. But because we may end up building a hash table that's larger than the amount of memory that's available to us because we're trying to join some large tables, then we're going to back that hash table by the buffer pool manager so it can spill to disk if we run out of space. Right? So again, the data structure will come out the next 2 weeks are going to be all throughout our system. And we're not going to want to use, in many cases, the things you can get off the shelf, like a third-party library or the STL, or pick your favorite Rust crate, because those are going to be typically not backed by the buffer pool manager. Right? They're going to be backed by malloc. We can override malloc, but it's still going to be OS memory that's ephemeral. System crashes, you lose whatever's in there. And if you're not in memory, it's going to start thrashing on its own. The OS is going to do that for you, and that's not. We don't want that to happen. We want to control everything. So there'll be two main decisions that we have in how we're going to design these data structures, because it's going to be slightly different than maybe you've seen in your previous algorithms class, because we're going to make trade-offs again about how we're going to choose what data structure, the internals of the data structure, based on the properties we said we cared about earlier in the semester, where we want to maximize the amount of sequential I/O rather than random I/O. So that means there'll be some things that may seem more inefficient to do versus if something was entirely in memory. But we're going to do that because we can convert random writes and random reads to sequential writes and sequential reads. And that's going to be faster for us. So today's class is we're going to mostly focus on the data organization side, like basically how we're going to represent the data structure internally, like the actual physical thing we're going to store in memory or on disk pages. There's another challenging thing we have to worry about, but we'll cover this in 2 weeks, of how do we make sure that our data structures are thread safe? Right? How do we allow for concurrent access, multiple threads reading and writing to our data structure at the same time, and doing in such a way that it's safe to do these operations and not worry about you changing some pointer address, and then all of a sudden some other thread reads that and goes off the middle of nowhere and you segfault. So for today's discussion and then Monday's next class, we're going to assume that our data structures are single threaded, and there's only one thread going to access them at a time. So we'll understand the basics, and then we'll see how to add latches and protect things later on. But there'll be other weird things that come up too. Why we don't want to talk about concurrency stuff at this point, because there's a higher level notion of correctness that we're not going to worry about just yet. But like, say if my one thread deletes something, I insert a key, some other thread deletes that key. Now I go back and try to read that same key and I don't see it. Is that correct? At the lowest level, the physical level, yes. At a logical level, maybe not. That doesn't make sense. Don't worry, we'll cover that later. That's not this class. All right, so like I said, the data structure we're going to focus on today is hash tables. And again, everyone should have taken basic CS classes that have described this before, so nothing I'm saying here should be widely new to anyone. But it's basically an unordered associative array that allows us to map arbitrary keys to arbitrary values. And at its core, the way this is going to work is there's going to be some kind of hash function, which I'll talk about in a second, that we're going to use to take our key, which could be any arbitrary length, run through a hash function. It then can compute some integer representation of that data. And then we're going to use that to figure out where do we want to jump to in our hash table to find the data that we're looking for, right? So the space complexity of a hash table is going to be O(n), where n is defined as the number of keys that I expect to store in my data structure. Now, in many cases, I may actually not store exactly n, right? I actually want to be less than that. Sometimes you say you just double the size you expect to store, and that's what you want to allocate it as. So n could be like the 2n of reality. For the time complexity, on average, it's going to be O(1), because we're going to assume that we have a way to take our key that we want to find, hash it, and then we jump some offset in our data structure, and lo and behold, there's the data that we're looking for. So average case is O(1). Worst case is O(n), meaning I have to scan all the keys individually one by one to find the thing that I'm looking for, right? So now, if you've taken an algorithms class, all the theoreticians see that O(1) and they start salivating, like, oh man, that's great. Oh, I don't care about anything else. And I think we sort of mentioned this earlier in the semester. In the database world, we do care about these constants. And even though it is O(1), there's going to be a big difference in performance based on how you actually implement these things, right? So if it takes me, my hash function is something really stupid, and it takes me 100 milliseconds to compute the hash to find out where to jump to find the data that I want, yeah, it's O(1), but like I can have a faster hash function that do this in 1 millisecond, right? And that's 2 orders of magnitude difference. For one lookup, maybe not a big deal, but again, think always in larger scales. If I'm doing 1 billion lookups, then that extra 99 milliseconds is going to add up. So in the database world, we care about constants because at the end of the day, that's going to equal money. Because if I can have a more efficient data structure, where even though it's still O(1), theoretical, but the constant time it is to do these operations is smaller and smaller, then I can store more data. I can run my workload on a smaller machine. And at large scale, again, you save real money. All right, so let's look at a sort of straw man proposal, the most simplest hash table you can imagine, of what I'll call a static hash table. All right, think it's just, again, it's a giant array of memory. And instead of calling them frames like we did in the buffer pool, we'll call them slots. And there'll be locations where in our array where we can store data. And so to make this work, we're going to assume that we know the number of keys ahead of time. So say big N. And to now find any key that we want, assuming we're going to be storing integers, right? We're just going to take whatever that key is, mod it by the n, the number of slots that we have, Actually, that could be, yeah. It's little n at the top, big n at the bottom. They're the same. Just ignore the difference there, all right? So I can take any key that I want, hash it, and then it'll tell me where that location is in my slot array. And then now I can maintain in the slot array itself, I'll have basically just pointers to some other location in memory or in other pages with the actual data that I want. Right? And I have to store the original key and the value, because if I start jumping into the array and I land at some location in my sort of data payload area, I got to know whether I'm actually looking at the same key or not. All right? So this is unrealistic for a couple of reasons. One is I assume that I know exactly the number of elements or the number of keys ahead of time. And in real world systems, that's almost never the case. Right? The way to get around that, you could do one pass of the data, count the number of records, then do another pass, and then populate your hash table. And some systems do that. But in general, we can't assume that's the case. And we can also maybe assume in some cases that the number of keys isn't going to shrink or grow over time. The other big assumption here is that we're assuming that each key is unique, and therefore, when I do my hash and I land in my slot array and it tells me where to go find the data that I want, I know that there isn't going to be something else in my slot array for another record that I need to find, right? And to make that work, I gotta basically allocate all of the possible key space that I could ever have, so n, even though I maybe not actually have it all, or maybe estimate may be wrong, but that's going to avoid having any collisions. And the last one is a slightly theoretical discussion, but when we run these hash functions, oftentimes we're not going to end up with like two distinct keys could end up hashing to the same value. And so there is a sort of class of algorithms or class of methods called perfect hashing, where you have a hash function that guarantees that there will never be any conflicts. And think of like if I have a number from 1 to 1,000, my hash function could just be returned that number because I won't have any conflicts, right? But if I'm trying to map a larger key space into a smaller one, then I can't assume that to be a perfect hash, right? So the way you do a perfect hash is you basically have to pass over the data once, make sure that there's no conflicts, and then sort of maintain another hash table that maps the original key to its location in the slot. So like I'm building a hash table for my hash table, and that's not entirely practical. You can cheat in some cases. You can say like, if I know the top 10 keys, then I'll have like if then else's that sort of bypass the hash function. But as far as I know, no system does that. Okay. So at its core, what is a hash table? Most people think it's the actual data structure itself, but it's actually a combination of things. The first is going to be what the hash function we're going to use, again, to take the arbitrary key space and map it to a smaller domain. And we'll see in a second, there'll be this trade-off between how fast we want our hash function to be versus how many collisions I could potentially have. And then the second piece will be the hashing scheme. So within my data structure now, if I have keys hashed to the same location in my hash table, what do I do? Like, what's the protocol to decide how to resolve that conflict, right? And we'll see sort of two examples how to do this, but there's a bunch of ones people have developed over the years. So once you have sort of the hash function, you have a hashing scheme, then you have the storage space you want to put the things, then you have your hash table. Okay? All right, so let's quickly talk about hash functions. I'll just give you the basics of what you need to know as when you build a data system. But the truth be told, we actually don't care what the algorithm is going to be. And I don't think it's worth our time to even discuss how to build a good hash function. There's other classes that do that. So for us, we're actually just use something that's off the shelf, right? And most of the newer systems are going to do this. Very few newer systems build their own hash functions, right? So again, a hash function is pretty basic. The idea is that it keeps a one-way hash. So given some key of an arbitrary length, we want to do some computation on it to then generate a random 32 or 64-bit integer, right? And again, the thing that we care about is we want something to be fast as possible and have a low collision rate. What's the fastest hash function you could build? Identity, faster. 1 or 0, and return a constant, because that's going to sit in a register, right? So if I pass you a string, I got to send you back the string. Sending back 0 or 1 would be way faster than that. But the collision rate is terrible, right? No matter what key I give you, no matter what email address I give you, the value is going to return 0 or 1. So that's not a good one. The opposite end of the spectrum would be that perfect hash function where I have a bunch of elaborate infrastructure to guarantee that no matter what key you give me, I'm going to give you a unique hash. Right? So again, the idea is that we're trying to convert these arbitrary length strings or whatever these keys we're putting in. We want to always then generate a fixed length value. So we don't care about any cryptographic properties of this hash function, and we don't care about the hash being reversible. So I don't care about taking whatever you hash me, the hash you give me, and giving back the original value. Right? This is all for the internals of the database system. We're not leaking any information on the outside. We're not worried about people, trying to do like an attack on us to like overload something or give me keys that always hash at the same location, so I slow things down. Right? That's not our problem. We're not worried about those things. This is all on the inside. We're not going to expose these hash values to the outside world. Yes.
So, a bit confused. A few lectures ago, we talked about record ID. You said an example of record ID is literally like the page and the slot number.
Yes.
So if you have the page and the slot number, you already know where to go, right? You don't need all this.
Statement is, earlier before we talked about if we had the record ID, and from that we can get like the page number and the offset.
Well,
why do we?
The record ID, the page number, and the offset, or can we get is that, or we can get the page number and offset from the record ID?
The record ID in some systems you are typically going to be the page number and the offset.
So then we wouldn't need this, right? Like
you don't need a hash table?
I'm asking.
No, you need.
We already know the page number and offset. Why do we need?
You don't. Wait, so hold on. So going back here, we're going to use this hash table for a bunch of things. This, right? So table indexes, just using that. That's the simplest one to think about. Think of something like a higher level key, like a secondary key or like a primary key. And the primary key is your email address. So I do a query, select star from table where email address equals yours. How do I then get the record ID that? The table index will give me that. Yes. But I also want to emphasize that the things we're talking about today, this data structure, isn't just for that. We're going to use it to do joins. We're going to use it to maintain other internal metadata. Your buffer pool manager in project 1, you guys are using what? STL unordered map or something, right? Well, again, if you crash, what happens? That map is gone. But say you wanted to make sure that you could replace that STL map with one of these hash tables that we're talking about here today and not use the STL one because you think you can do a better job than that. And you usually can. Although the Google data structure library AppCell is actually pretty good. The Facebook follow one's pretty good too. But again, that's not going to be backed by our buffer pool manager. All right. So again, we don't care about cryptography. We don't care about denial of service attacks. This is all in the internal. We're not exposing the outside world. So I just want to quickly talk about what options are available to you. And it's almost 20 years now, but there's sort of there was this resurgence in interest in hash functions for database systems in 2008, started by MurmurHash. And it was like some random guy on GitHub or something just posted like, here's my really good hash function. And a bunch of database systems picked it up and started using it. And over the years, there's been improvements to it. The main takeaway is going to be the state-of-the-art one that's considered the fastest right now is RapidHash. But as far as I know, no database system uses RapidHash yet because it's like too new. Most of the newer systems are going to use XXHash or XXHash3, right? So in general, this is what you're going to want to use. And that's it. That's all you know about hash functions. String in or data byte array in, 64-bit integer out. XXHash should be fast. Let's use that. Okay? You could use RapidHash. I'm saying, sorry. Their statement is, why can't we use RapidHash? You can. So maybe state-of-the-art is both of them, but nobody uses this one yet, as far as I know. I haven't grepped all of GitHub to see where it shows up in any database system because we have all the GitHub accounts. We have all the GitHub URLs for every database system that's open source, so we could check. But I think we checked last year and nobody was using it. All right, so again, assume we have some hash function. For our purposes going forward in this rest of this lecture, we don't care how it's actually being implemented. We just know if we give it some byte array, we'll get some integer out. Okay? All right, so first we're going to talk about static hashing schemes. Again, the idea here is that you specify when you allocate the data structure, the number of potential locations where you could want to store records, store information, the number of slots that you want in your implementation, right? We'll see dynamic hashing in a second, and again, that'll be a hash table that can grow and shrink with more or less keys over time. But static hashing, you sort of allocate things at the very beginning, and that's it. So we're going to talk about basically the two most common approaches, linear probe hashing and cuckoo hashing. Linear probe hashing is used everywhere. It's the most common one. It's actually the most simple one. And this would be a good example where simple is actually better. It's actually more performant than all these other fancy ones. So if you take the advanced database class, we'll cover all the various things people developed over the years: Robinhood hashing, hopscotch hashing, twist tables. There's another category of hash tables we're not talking about in this class called concise hash tables or memory efficient hash tables. And this is where, again, you're going to be doing a hash join, and I'm going to build my data structure, then immediately throw it away. So I want something that is compact as small as possible, because I'm not worried about building the hash table and then an hour later someone come along and trying to insert something into it or delete things. All right. So the one thing I understand is that the terminology starts to overlap and gets kind of confusing with these things. So I'm going to be talking about linear probe hashing, and there'll be another hash table called linear hashing that I'll cover at the end of the class. That's a dynamic hashing scheme. Linear probe hashing is a static hashing scheme. And these are also used in a category called open addressing algorithms for hash tables. And this just basically means that the location of a key in my hash table is open, meaning it could be anywhere. There's no guarantee that if I insert the same key if I insert the same key in my data structure at different times, it's always going to be in the exact same location. It's allowed to be in different locations. And so the hash function is basically going to give us a way to jump into the hash table, at least as a starting point, and then we may have to look around, scan some data to find the key that we're actually looking for. There's no guarantee it's going to be exactly in that location. It'll make more sense when I show examples. Again, linear probe hashing is the most basic one, but it's used in a lot of systems. All right, so the way to think about the hash table is just, again, a giant table of fixed length slots, and it can be backed by pages in our buffer pool manager. And so what's going to work, how's it work is that when we hash into our hash table, if there's another key in the location where our key wants to go into, then we know that space is being occupied, and we have to scan down linearly, like looking at one slot after another, till we find a free slot. And once we find the free slot, then we can put our key in, and then we're done. All right? And insertions are basically, deletions are basically, insertions and deletions and searches all sort of work the same way. We do have to keep track when we start scanning through, where we started when we entered the hash table. So, because we'll loop back around, if we come back to the original location, we don't want to get stuck in an infinite loop because we know the hash table is full. And then depending on what our operation is, we may have to stop what we're doing and resize things. So in most implementations, there'll be this notion of the load factor, which is basically the number of actively used slots divided or over the number of total slots. And when that gets above some threshold, then the system will say, well, I think I'm getting too big and I'm going to run out of space. Let me halt any operations. Again, assume you take a global latch on the whole data structure. Allocate a new hash table that's twice the size of the original one. Take all the keys out and put it into the new one. That sucks. That's really slow. This is, again, why you typically allocate the hash table would be a little bit larger than what you expect to actually put in it, so you don't have to do that. But some systems allow you to play around with this load factor to say, like, I'll allow myself to be 99% full before I have to resize. All right, so let's go over a simple example. So I'm showing this on PowerPoint. Again, it's a diagram, but assume that this data is being stored in buffer pool pages that are being backed by disk. So I have my hash function, and then I have the n defined as the number of slots that I have. So if I want to insert key A, I'm going to hash it, mod by number n, and it's going to land in that slot there. And in this case here, my hash table is empty. The slot is empty, so my key A can go right in there. And again, I have to store the key and the value together. The value actually may be a pointer to something else. We'll cover that in a second. But like, I need the original key because if now I start having collisions and I start changing the location of where the key I'm actually inserting is, not the original one where I started off, then I need to know whether the slot I'm looking at contains the thing that I want. I insert B, hash to the top, that's fine. Now I insert C. Now I have a collision. C wants to go where A is, but it can't because A is sitting there. So we basically recognize that the slot is occupied, do a linear scan to the next free slot. We see that it's empty, or the next slot, see that it's empty, and then we can go ahead and insert our key there. Same thing for D. D wants to be where C is. It's occupied, so it has to scan down and put D there. E wants to go where A is, can't go where C is, can't go where D is. We finally find a free slot there. And just to finish off, we'll put F, wants to go where E is, and it goes to the bottom. Right? Pretty easy, right? And because we're doing a bunch of linear or sequential operations, right? If I have to read multiple pages from disk, I can read these pages in sequential order till I find the free slot that I want. All right, so how do I make sure that that my entries or the data I'm storing is going to be fixed length, right? So if the data I want to store is fixed length, then I can just inline it with the data structure itself. So I can also store the hash to sort of make things go faster, right? Because I want to compare the hash with whatever I have in there plus the hash of the thing I'm trying to put in there. I can store the hash there, but it's space versus compute trade-off. Right? Takes more space, but makes the lookup go faster. But if my value fits in just fine, and I can just store this inline. Obviously, I don't want it too wide now because now the size that I'm jumping from slot to slot gets really big, and it can become wasteful. Yes.
Just to clarify on the previous one, if you want to access a key value, so this is storing it, but if you want to access it, you run through hash function and then do a sequential scan to find that key.
Yeah, his question is, this is doing inserts. How do you find things? It's the same thing, right? So say I have F. I want to look for F. I hash it. I land where E is. E's not what I want. I keep scanning till I find the value that I want, or a free slot, an empty slot, meaning because I know my key can't be in there because if it existed, I would have seen it when I was scanning through. That's as we said in the beginning, ON. Worst case scenario, I read everything. Keep track where I started so I don't keep going. Yeah. All right, so if our data is small and it's fixed length, we just store it in the hash table itself. If our data is variable length or too big, then we'd end up basically store some kind of record ID or a pointer or something to a temp page, and just have the data we want be chucked in there. If we're storing this as an index, like a table index, then the record ID would just be to the original tuple. But if again building a hash table for a join, I don't want to maybe reference the original data because I might have manipulated or done some other joins prior to that. So I need to sort of temp pages to put data that I want. But it's the same mechanism to have a pointer to say, okay, you want the value after you find a match, here's where to go find it. Yes?
So, variable length value that's always stored in the template page. Wouldn't like you have like a JSON entry or a tuple, wouldn't you need like something more permanent?
This question is, if you have a JSON field in a tuple, when you
You can have a JSON.
yes, yes, but it's like if it's variable length, I don't want it in the. I can't put it in my slot array because it breaks the whole mechanism of taking the hash of the key and then modify the number of slots. So it's variable length. I'm going to jump to random locations. I can't do that. So I can't put it in there. I got to put it somewhere else. So I'm just saying here is like you just have this sort of temp thing where the key that you're trying to do lookups on is now in this other temp space that could be variable length, could be slotted pages or whatever you want. Doesn't matter. And then now in my hash table, I'm storing fixed length record IDs. So his statement is, and he's correct, like when you want to store the keys in the hash table to make it fast as possible, yes, but if they're variable length, you can't do that because now all your slots, yes. So the trick you could do would be, say you're storing variable length strings, I could take the first like 8 characters, store that in my hash table, right? Still need the record ID to get the original one, But at least now I can just look for the prefix and see whether that matches. What's that? This is German strings, yes. German strings basically says, like, instead of when we had that the overflow page, we had the we didn't want to inline the variable length data. We had a pointer to it, but in order to see if I have a match on that variable length data, I got to follow that pointer. So I can, again, just store a prefix to do that early matching, right? And it was invented by the Germans. I called it German strings, and apparently that's the term everyone's using now. But yeah, German strings. All right. So not all the hash tables in our systems won't care about deletes, but again, if they're table indexes, you do. So how are we going to handle that? So the idea, again, so say I want to delete key C. So I do my hash, I mod it, I land where A is. A is not the key that I'm looking for. I jump down to C. Here's C. I want to go ahead and delete it, and I can just remove it. Yes?
So when the load factor gets large, you expand the size, you rehash.
The statement is, when the load factor gets too large, without deleting, just terminate in general, or this example here.
No, in general, you resize
Yeah, the question is, when the load factor gets too large, do I have to resize the table? Yes, you allocate a whole second table, scan through, and hash everything, put it back in the new one. Yes. Dynamic hashing won't do that. We'll see that in a second. All right, is this a good idea or a bad idea? What did I do here? I deleted key C. I just removed it from my slot.
Obviously, you have the problem that if he was a collegian, he can't find it.
Yes, he's pathetic here. So the statement is, if now something wants to do a lookup on D, well, D is going to hash where C was. Because it was occupied when we tried to insert D, it had to go to the slot below it. So it's going to hash here now, land to where C used to be, see that it's empty. And again, the protocol for deciding whether a key exists or not is I keep scanning until I find it or I see an empty slot. Then I'm done. So it's going to see an empty slot right away and think that nothing's there and we're screwed, right? So there's two approaches to handle this. One is basically what we talked about before, but like resizing the table. You basically just move everything around. So you figure out what the key you deleted, scan everything afterwards until you find the first free slot, and rehash everything you see to figure out where it actually should go. So you're kind of like dumping out a portion of the table and inserting it back in, right? You could be stupid and start moving things around. You could just move things, but that's not going to work because things may not. You have to rehash to decide whether it actually should go where we want to point things. So in this case here, looking up D would be fine. It would still work. E would work as well as F, right? But then the tricky one, of course, what would you with B? Do you wrap B around or not, right? Doesn't matter. Okay. So nobody does this. Don't do this. This is just way too expensive because, again, you don't know how many things you're going to have to rehash at the moment you do this, right? So what you really want to do is just use tombstones. And you basically maintain a little marker to denote that the key that used to be here has been deleted. It's not physically removed, right? I mean, you could zero out the bits if you want. Doesn't matter. But when you do a scan, the thread's going to see that the space used to contain something, but it's not there anymore, and it knows to treat that as if it was occupied and not really a truly empty space. So keep scanning to find the things you want, right? So I delete C. Hash to A, go down here, mark a little tombstone. Now when I do a lookup on D, D lands where C used to be, sees that there's a tombstone, and says, all right, well, something used to be here and it's not anymore. Let me just go ahead and keep scanning until I find the thing that I want, and then I'm done. And occasionally there'll be some background thread if you wanted to go ahead and prune these up, and in which case you would have to do rehashing if you wanted that. Or if now someone wants to insert something to the space that is occupied by a tombstone, you can just use it. And that's still considered valid and correct. What's that? If I do what? The question is, what would happen if I query to get C? Well, it would, in this case here, you would see what hashes to A. So you land at A. Say this is not the delete, this is the get. I would see A is not what I want. I would keep scanning. I would see the tombstone spot on C is. I know that's not what I want either because it's considered deleted. And then I had to keep scanning down D, E, F, wrap around to B, Then I get to that first free slot up there. It's empty. At this point, I didn't see C, and I would have seen it if it was as I did my scan. So I would say it's not found. Yes.
So, if you want to write update PP here, how can we tell difference whether we should just directly override the console or just find it somewhere else?
The question is, if I do an update to D or insert a new D.
Update the value.
So same as what would I do if I update the value of D? I mean, for this, we wouldn't. For updates, you scan the key they're looking for. If it doesn't exist, you don't update it. If you do see it, then you could just overwrite it, and you wouldn't need to move where D is. We're not really about updates. We're not worried about here. It's insert, update, deletes. Or sorry, insert, deletes, and selects, or gets. All right. So now let's say I want to insert a new key G. G hashes to where C used to be. Again, it's the tombstone's there. It knows that logically the space is unoccupied. So let's go ahead and put the thing we want in there. So you wouldn't typically store the tombstone in line on in every slot. Typically, it'd be like in the page header. You would say, here's all the slots and whether they're considered occupied or not in a simple bitmap. And that ensures that all your data is aligned. Yes? The question is, am I going to maintain a map about tombstones or what? The question is, do I need to maintain a separate data structure that says for a given key, it's been deleted? This is the data structure, right? So the question is like, do I need to record that this tombstone corresponds to a previous value? But like I suppose you could do that. That would help prevent the problem I said before. Like if I look for C, I then have to wrap around. I could just see the tombstone. Oh, C used to be here, and that's what I'm looking for. I guess it's not here anymore, right? The problem with that one is though, you don't know whether someone else inserted C after later on, and I would miss that if I saw the tombstone immediately jumped out. I think you're saying, like, are we relying on information that we can store in the tombstone to help optimize certain things? I think that's essentially what you're saying. I suppose you could. Nobody does that because it's extra complexity, and this is so simple that it just makes it so fast. Like the extra checks you're talking about are just probably not worth it, right? I might be wrong about that, but if most people don't do that because most people are also going to not support deletes anyway because they're going to use these for hash tables where I'm just inserting and then reading and then throwing it away. But if you want to support deletes, that's an additional optimization I'm thinking you could do, but I don't think anybody does it because it's just more machinery. Okay, let me jump through because we're short on time because we haven't got the dynamic stuff. But if you want to handle non-unique keys, you basically have this. You can store them either in separate linked lists or you just store the key multiple times. That's what most systems do. The second one. The tricky thing, of course, is going to be that if, depending on the operation I'm doing, I may see, say, go give me key XYZ. I may hash into it, land it, see key XYZ. I have to keep going until I see the first free slot in my lookup, because at that point, then I know that I'm not going to see any more XYZs. Right? Same for deletes. If I want to remove all the XYZs, I have to do that. Again, most systems do that because you don't need to maintain the separate data structure up above. Just store my keys in the giant hash table. Right? Let me skip optimizations. Just to say, like, you could have specialized hash tables based on the keys. So in ClickHouse, for example, they have hash tables for strings, have separate hash tables for integers. They have separate hash tables for large strings, right? They have 20 different hash tables in their implementation, which is crazy. So they have an amazing blog article that talks about a lot of these things. All right, I'm going to talk about an alternative to linear probe hashing called Cuckoo Hashing. And this idea should be pretty simple, but it's again breaking this conceived notion that like we're going to have one hash function to tell me one location where I can find my find the key that I'm looking for. I'm actually going to have multiple hash functions, and my key can be in multiple locations. And it may change over time, because again, the open addressing allows me to do that to over time as the keys that I'm inserting changes. So the lookups and deletions are always going to be O1, guaranteed, because I'm going to, if I hash it, I'm either going to find exactly the key I'm looking for, may have to hash it multiple times, still constant factor, but again, that's not free, or I'm not going to see it at all. The inserts are going to be more expensive because I may have to take a slot for somebody else, remove the key, and then insert it back in. Let's look at an example. We'll see what I mean. So I want to put A. I have a single hash table like I before with a bunch of slots. But in this case here, I'm going to have two hash functions, right? It's going to be the same implementation, like same rapid hash or XS hash 3, just you give it a different seed so that they guarantee to produce, or not guarantee, they're going to produce different hash values. So I'm going to hash both of them, the key twice with both the hash functions, and I'm going to end up with two different slots. And I'm going to look to see which one's empty. In this case here, I'm completely empty. I'm going to flip a coin and choose the first one. And that's where my key is going to go. Now I'm going to do the same thing. I'm going to hash B, two different locations. The first one, the first hash function, is occupied by A, so I'm going to ignore that. And instead, I'm going to choose the free slot that the second hash function has, or points to, and I'll get B. Now let's see an example where I have collisions at both locations. So hashing C, the first hash function is where A is, second hash function goes where B is. Both are occupied. So the way this is going to work is I'm going to choose a victim. I'm going to choose one of the slots that I'm hashing to. I'm going to steal their location, kick them out of the house, put my shit in there, right? And then they got to go find a new place to live. It's called cuckoo hashing because there's like a cuckoo bird. That's what they do. They go find other birds' nests, kick them out, and then plant their own eggs, right? Basically, what's that? The question is, where did the victor entry go? Let's keep going. This. Yeah. All right, so we're going to take the first one. So C is going to kick out B, put his stuff in there, and then now we got to put B back in, right? So with B, I'm showing, for simplicity, I'm showing only hashing with the first hash function, because back here, right, we decided to choose the second hash function. In actuality, you're not going to record what hash function you used to insert it, because there's extra space is unneeded. You would end up hashing it again, and then see which one is occupied or which one points you to the place you just got kicked out of, right? So now we hash B again, the first hash function. It goes where A is, so same thing. It's going to take its slot, kick A out. Now we get A back in. We're going to hash A, and it's going to land here, and that was the free slot, one of the free slots we had in the very beginning. How to what? How to prevent cycles? You just keep track of like, hey, this is the key I just inserted. I'm trying to, that I started off with. Statement is the list was quite long. Yes. It's like, no, it's not a list. You don't need a list. I don't care about how I got there. I just care what the key I started with. To his point, yes, you're right. So I don't know exactly. I don't think you don't need the full list though. I think you need where you started and the most recent one. Yeah, no, you could have. I don't know the answer, but it's going to be. If you have to maintain the list, it's unavoidable. Yes.
So what if like they collide on all hash functions?
Same as if they collide on all hash functions, the hash table is full, double the size, and rebuild it. Yep, no free lunch. You always have to do something. So now I'm going to do a lookup. I want to get B. I'm going to hash it twice. Again, I'm showing this being parallel because it's PowerPoint. In actuality, you hash the first one, see whether it has the thing you want. If it's there, you're done. Then if not, then hash the second one to see it, right? But in this case here, I would hash the first one, look for B, and I would find it in my slot there. But I could also look at the other one. And that's why it's O1. Because I'm guaranteed to either see it immediately in my first sort of step into the data structure, or it doesn't exist. Yes? Go back here. So we were here. C collided. We want to insert C. C collided with A and B. We got to pick a victim. evict B, yes. C goes in there, B pops out, we got to put it back in.
Why can't we check both? Can we hash B with both functions and then check if either of those are the same?
If either of them are the same?
So hash B now with hash function 1 and 2.
Yeah.
Check if either are empty.
Well, so the second hash function is where I came from. Yes. So you would do both of them when you come back out and try to go back in, because it's this the protocol is the same if you're inserting a key for the first step versus like I got evicted, I got to go back in. It's the same. And for PowerPoint reasons, I'm just not showing. Yeah, but you would do both. Yes. The question is, how do you know how many hash functions to use? Yeah. So I think there's been theoretical work done on this. You can prove that like for a hash table this size, this many expected keys, you want this number of hash functions. And then there's a trade-off also too, like if I have a lot of hash functions, then I may, it's more work, but I can maybe not hit a cycle as quickly, right? I forget the default one. So the best open source implementation of a Cuckoo hash table was actually from CMU, from Dave Anderson, and they still maintain it. And I think the default is like 6 hash functions. Other questions? So this is a neat little trick. It's a cool idea. It's slower than a linear probe hash table because linear probing is so simple that you can rip through it quickly. So very few systems do this. All right, so in the 2 schemes that I showed, you got to know the number of keys ahead of time, right? And then if our load factor gets too much, or we get stuck in an infinite loop in the Cuckoo hashing, or we run out of free slots in our linear probe hash table, we got to stop what we're doing, reallocate space, and resize it, right? So dynamic hash tables are going to have a mechanism built in that allows them to grow and shrink incrementally as needed as you're inserting things. So the hash table you're probably most familiar with is chained hash table. I think this is what Python gives you, or Java hash map gives you, right? But in the database world, there's 2 more sophisticated ones: extendable hashing and linear hashing. And again, I was saying the confusing part is I just took the linear probe hash table, and there'll be now a linear hashing hash table, and they're separate things. One's static, one's dynamic. I don't make up these names, right? I don't have control. All right, so chain hashing. Right, this is what you get in Java hash map. Actually, Python. I don't. Python gives you this by default, but this is what Java gives you. So you're basically going to maintain a linked list of buckets for a given slot where you can insert keys. So it's kind of like a partitioned version of the linear probe hash table, where you still have to do a sequential scan potentially to find the thing you're looking for. But at least now you don't have to scan the entire table. It's just scoped into the some portion of the table. And you resolve collisions by just placing elements that collide with each other. You're going to append them to the end of this bucket linked list, right? As you define the key that you're looking for, you hash in some linked list, and then you scan through and see whether the key exists or not. So now we're going to have this separate data structure of bucket pointers, and then here's going to be all our buckets, right? So I want to do a put on A. I hash it mod n by the number of bucket pointers I have. And that's going to then give me a pointer now to the starting location of the bucket chain. And now I just do my linear scan, linear probe to find the first free slot. As soon as I find one, I can put the key that I want. So I'll put A there. Same thing, I want to insert B, hash in the bucket pointer array, find a location, and we put it there. Now we want to do put C. C ends up in the same bucket list or bucket chain as A. But it scans through and sees A's occupying the first slot, jumps down to the next one till it gets it, right? And then same thing with D. D goes where A and C are. But at this point, our bucket, for simplicity, only has two slots. So we have to make a new bucket and just have a pointer from that bucket to the next one, all right? So obviously, this bucket chain can grow infinitely. And so if I'm unlucky and my hash function is terrible, they're all mapping to the same location, then it's going to be, again, on lookup for everything. And that's going to be bad. But the hash function, if it has low collision rate, then I'll have some more randomness and things will be more evenly spread out. Same thing, put E, so forth, goes in here, put F goes down here, right? So one little optimization you can do that some systems do is you put a little filter in the bucket pointer array, similar to that prefix in the German strings that I just mentioned, where like I can check this filter to say, hey, is the key I want, could it even exist in my bucket chain that I'm going to point to? If yes, then I do the scan. If no, then I don't even bother doing the scan. So typically you're going to use something like a Bloom filter. It's okay if you don't know what a Bloom filter is. We'll cover that next week. But it basically, it gives you like set membership. It just tells you, does this thing even exist or not? And it may give you actually a false positive. It may tell you it exists when it doesn't actually exist, but it'll never give you a false negative. And it'll never say this thing doesn't exist when it actually truly does. All right. Let me try to plow through in 13 minutes one of the two hardest data structures, but we can revisit this again on Monday next week again. All right, so extendable hashing is a more sophisticated dynamic hashing scheme that extends or builds upon the chain hashing approach I just saw before, where when I want to start resizing the data structure, I'm going to split buckets. Instead of just letting this linked list grow forever, which again could end up being ON, when my bucket gets full, I'm going to split it and redistribute the keys inside that bucket. So at most, the bucket chain can't grow forever. Every chain is going to only have one bucket in it, right? But the game they're going to play is, to make this all work, is they're going to allow in our bucket array, multiple locations in that bucket array could point to the same bucket. And that's going to be okay, right? So this is not widely used. It's an older technique. It was in there's a GNU database management system. Think of like an embedded key value store that like the GNU environment provides you. It's also used in DB, which is a big data system at UC Irvine from 10 years ago, but I think got merged into Couchbase, and Couchbase uses a lot of these techniques now. All right, so let's see what this looks like. Okay, so for every bucket, there's going to be this sort of this local indicator saying how many bits do you have to use to get to that bucket, and there's going to be this global bit counter thing that's going to tell me globally how many bits do I need to consider at this point in time based on the size of my hash table to find a particular bucket for a given key. So it's basically determined that it's the maximum number of bits we have to consider in our hash. So again, the hash function is going to return like a 32-bit integer or a 64-bit integer. But the way this scheme works is, at least as you start building it up, as growing and resizing things, you only need to look at a small portion of those bits at the very beginning, right? So in this case here, so the global bit counter is 2. So that means that I only need to look at 2 bits in my hash value, right? And so this global thing is going to increase anytime I'm going to start doing splits. I need to resize things. But then the local bit counter, it's just sort of keeping track of, like, for this bucket, how many bits did I actually use to get there. But the way we're going to get into it, we need to use the global one and the hash bits and the bucket array on the side here, right? All right, so let's so sort of think of it like this, right? So for these first 2 elements or first 2 locations in the bucket array, I only need the first bit, but for the other 2, I need to look at all 2 bits. Okay? So let's first do a lookup on A, right? So the first thing I do is I hash A. I get back now a 64-bit integer, made it for 64 bits, but I look at my global counter, my bit counter, and it's set to 2. So I know I only need to look at 2 bits to find in my hash table the bucket I want to have this potential key, right? So the first 2 bits are 0, 1. So I look in my bucket array for 0, 1, follow whatever that pointer is, and I land in that bucket that I want, right? That's pretty easy. If I want to do a put now, I'm putting B, same thing, hash it, look at the first 2 bits, right? It's 1, 0. That takes me to this bucket here, and because I had a free slot, I can go ahead and insert it without spilling, and that's fine, right? Now let me do a put on C, and now when I hash it, the first 2 bits are 1, 0 again, and that's going to take us to this bucket, but there's no more free slots for it inside the bucket, so now I have to overflow it. So the way this is going to work is that I'm going to increase my global bit counter to now 3. And now I'm going to create a new slot array here that's going to be double the size that I had before, because I'm now going to include an extra bit in the addressing scheme for it, right? So this thing's not that big. This is not like resizing the giant hash table of all my keys. This is a small operation. This is no big deal, right? So now I'm going to resize it. And now the global bit counter is 3, but I have a bunch of other, and I have that middle guy, that middle bucket I need to split. But for the one at the top and one at the bottom, I'm going to leave them alone because they're not being modified by this insert, right? It's only that one in the middle. So I'm going to go ahead and split the middle guy, right? And then go through and rehash the keys that are in it to decide where they need to go next, right? So now in my bucket array, I know that I have a bunch of locations here where I only need to look at the first bit, and that's going to take me to that first location here. So bit is 0, you just go there. Then I have these other ones here. You need to look at 2 bits, and that's going to take me to this one, the one down here. And then for 3 bits, those will be separated into those separate ones here, right? Yes, question?
Is the number next to the bucket just tracking how many times it's been split?
Yes, the question is the number next to the bucket keeping track of how many times it's been split? More or less, yes. Yeah. Yes.
Have some like pathological data that like makes the global table status code.
The question is, could you come up with a pathological case where this thing just grows exponentially because everything's hashed in the same location? Yes. So, like, how to say this? If you have a table that has 1 billion records, and you're trying to build a hash table on one column, and that one column only stores the value 1. It's 1 billion records that all have the value 1. Yeah, this is gonna be terrible for this, right? Don't do that, right?
Are you maintaining another list to track which ones are for 1 bit, which ones are the 2 bits of buckets, which ones are the 3 bit buckets?
The question is, am I keeping track of like which one is a 2 bucket one or what 3 bucket one? No, so you implicitly get that. So I'm showing like, these numbers here, the 1, 3, 3, 2. But this is for demonstration purpose. The pointers themselves, because I'm allowing multiple slots to point to the same thing, right? So because I haven't split the first bucket yet, then if anything hashes to any of those slots here, implicitly I know I only need to look at the first bit, and that takes me to that one, and they're all pointing to the same thing. Yes?
So I have 2 questions. First, you said when we overflow, we don't want to touch 1 and 2, we want to split 3. But must we split 3? Like, can't we just redirect like the 1/2 of 3 into 1 and the other half of 3 like we did?
So his statement is, in this case here, when I have to overflow and split 2, instead of splitting it, you're proposing to do what? To
Redirect 1/2 of 3 into 2 or 1.
what do you mean redirect?
Like the second array label.
Like this thing here.
Yeah, like can't we? Well, okay, the first one, the top, the first array number 3. Then
Yes.
can't we just merge it with number 1, for example, and not split any of the others?
A statement, can't you just merge? A statement is, could you just take the second from the top, merge it back into 1? No, because the hash value to get into that second one.
So you would still change the left-hand part. Like you would still like have more bits now that you look at. It's just 100 goes into.
I understand what you're saying. I'd have to think about whether it's correct. You could do it, but like you.
Like, don't you want to decouple?
So this goes back to what I was saying before. it isn't like an algorithms class where you assume everything's in memory. That top page, right, like the one with the 1 on it, that may be out on disk. So to do what you're proposing, I got to go still create the new page, right? So there's one allocate there. Then I got to go read that other page, bring it back in, and do a write to it again. It's just that extra machinery is just not worth it.
Fair enough. And my second question was, don't we want to look at the least significant bits? Because isn't that like more random than fair?
Same as, you want to look at least significant bits? Wouldn't that be more random? Depends on the hash function. Okay, it's after being hashed, right? So the hash is supposed to generate a
Right. So
like
those are the results of the hash function.
yes, yeah, it's random. So his statement is, and he's correct. Like when we talk about bit packing, remember he said like, oh, like you sort of think it's a 32-bit integer, but most of the front of the bits are going to be 0, and therefore that's sort of wasteful. You're basically with the hash function, you're generating random integers for arbitrary keys. So like the string A and the string B, those are pretty close to each other if you just look at the bit sequence. But if I take a good hash function, they may be completely different hash values. Therefore, the bit sequences are completely random. So I'm just showing you whatever the most significant ones here. Okay. So all right, let me get through this last one, linear hashing, and then we'll switch over to the guest speaker. So that is the same, that we want to be able to resize our hash table without having to rehash everything. This is going to be slightly different now, where we're going to allow we're going to trigger a resizing when a bucket overflows, but the bucket we're not going to split is not potentially not be the one that overflowed. In extendable hashing, the one that overflowed, that's the one I split. In linear hashing, it may not be the one. We'll see why in a second. So this is actually what Postgres uses. I think they called it the dynahash table or dynamic hash table, something like that. The code that was written in this was written by one of Mike Stoneberger, the inventor of Postgres' students back in Berkeley in early 90s, late 1980s. She then went off and re-implemented a linear hash table in this thing called YugabyteDB that Oracle bought in 2006. And then this is actually an internal data structure that DynamoDB uses as well. All right, so just like before, we have bucket pointers, and they're going to point to buckets. But now I have this extra thing called the split pointer, and that's basically just me pointing to some bucket that's going to be the next bucket I'm going to split whenever any bucket in my hash table overflows. So at the very beginning, I'm always going to have a powers of 2 number of buckets. In this case here, it'll be 4. And I'll have a hash function that I can have multiple hash functions that I'm going to use to decide where in my bucket pointer I want to jump into based on the location of the split pointer. This will make more sense in a second. So say I want to get 6. I take 6, I hash it. Say we're just doing the identity hash, so it's the same value. And I'm going to mod it by the number of buckets that I have. In this case, 4, and I end up getting 2. And so when I look at my bucket array, I would see that that bucket is below where the split pointer is pointing at. So I know I only need one hash function to find the thing that I'm looking for. So then I just jump along, in a bucket, do linear scan to find the thing that I want. Now let's say I want to do a put on 17. I mod it by 4, I get 1. Now when I land in this location here using the single hash function, I see that the bucket is full. So now I got to do I have to add an extra bucket to my chain and keep track that I overflowed. So that means I'm going to split something. But the thing I'm going to split isn't the thing that just overflowed. I'm going to split whatever the split pointer is pointing at. In this case here, it's pointing to the top bucket, bucket 0. So I'm going to go ahead and split this guy. Even though it has a free slot, and it could absorb another insert, I'm still going to split it. All right? So now to do this, I'm going to add an extra entry into my bucket pointer array. So now there'll be slot 4. But now I can't address that if I do mod n, what it was before, which is when I had 4, right? Now I'm going to mod it by 2n, whatever I had before. So even though I haven't added any entries into my bucket pointer beyond just this fourth one here, I know I'm going to keep growing. So I have to add new entries as my split pointer moves down. So in this case here, I have my new hash function. Now I got to go figure out where to go put all of the keys that exist in the first bucket that I split. So I take key 8, mod it by now 2n. So this is going to get by 8. So 8 mod 8 is 0. So that's going to stay where it started. But then 20 mod 8 is 4. So that's going to now point to this one down here. All right, so I'm going to move 20 down here. And I move the split pointer down by 1. Now I do a lookup on 20. First I'm going to do is take the first hash function, right? So take whatever the value is, mod by n, and that's going to land me in location 0, because again, that's where it was before with the first hash function. But here, now I check to see, is the location with the first hash function above the split pointer? If yes, then I know that the bucket had been split. So therefore, I have to hash it again using the second hash function to find where its current real location actually is. Because I don't know, after I do the first hash function, whether it remained at the top or got moved down to the one at the bottom. In this case here, 20 got moved to the bottom. You're shaking your head no, as if this is terrible.
I just can't imagine that this is like more efficient than the other one where you're splitting the bucket that's overflowed. Because I would imagine, like, say we have like this now, like bucket 1, like this is now not the one that gets split. Right?
Yeah, yes.
Like we have to do the rehash of 17. That still goes in one, but we have to, like, when we do it with 5, 9, and 13.
So yeah, so this sounds crazy. Like, why would you do this? The idea is that eventually, if I overflow again, then I'll split the one that I built the chain on. So eventually it all evens out, and you can end up sort of with a balanced data structure. Yes?
So the new hash functions are always like you multiply the mod by 2.
By 2n, yes. So yeah.
And you move the pointer
Whenever you split something else. All right, last question. Sorry.
How do you handle the case where you haven't split a sufficient number of times and so you end up out of bounds? Your rate is like 2n, you end up with like 7 here in this example.
The question is, how would you ever get out of bounds? Like, the array actually exists. You just haven't allocated buckets for the things below it yet. Yeah. All right. Sorry. We can come back to this on class next week. We'll pick up on it again. Let's switch over to Karthik. All right. This is Karthik. He's the co-founder of Yugabyte. It's been 10 years, right?
It's getting there. Almost 10 years, 9.5. Yes. It takes 10 years to build a database, so yeah.
Which is
fighting it. It is right.
Which is insane. All right, floor is yours. Thank you for being here.
So folks that are not familiar with YugabyteDB, we convert PostgreSQL. It's a new database. We've taken Postgres as the source code and we made it a distributed database. And we're fully open source under Apache 2.0. And we've had quite a few members in the community contributing, a lot of deployments, et cetera, and we are a distributed cloud native version of Postgres, right? These are some of the things we focus on: distributed transactions, multi-API, cloud native, and getting, supporting AI workloads. We look at a few of these things, right? So what are we really? As I said, distributed, fully Postgres compatible database. We're built for business critical applications, right? And we focus on bringing resilience, scalability, and geo-distribution or multi-region deployments to Postgres. And this helps people build modern applications. You can think of multi-region, GenAI, Edge, these type of applications, or to modernize their existing applications that are high value but want to come into the cloud native world. Our thesis, why, it's always important to ask yourselves if you know why a database exists. We ask ourselves that, and what is the differentiation? So if you think of y-axis as how Postgres compatible a database is, and the x-axis as truly how cloud native a database is, we were born to be at the intersection of those two. There's a line on the y-axis after which you're reusing Postgres code, and those databases continue to benefit from Postgres and inherit most of the Postgres innovations. There's a line on the x-axis, the cloud native database innovation threshold, to the right of which you can truly go and build cloud native systems, right? To put names to faces, if this is our thesis of the market, you can test it out yourself. You obviously shouldn't trust me. I'm a founder, so you should trust only so far as it goes and extend your own ideas to this. But anyways, the ones above the PG innovation threshold reuse Postgres code, therefore can build along with the Postgres innovation. Otherwise, you're building to it. And those to the right of the cloud native innovation threshold are architected from the ground up to be shared nothing, cloud native, highly resilient and available, right? And so we were born after most of these databases. So hopefully we got something right, which was to hybridize the best of those two into a single product. Okay, these are again our areas of innovation, Postgres, distributed, enterprise grade, AI, right? We have a lot of customers, won't bore you with this. I'd like to talk about just one customer here, NPCI, which is the National Payment Corporation of India. So all mobile payments in India are going through a Yugabyte database. Very proud of the achievement as a product, as a company. But anyways, just something to show that, the level to which it waxes and wanes, the level to which you need resilience. It is truly the case there that resilience, availability, uptime, and scalability equals money, right, in this example. Okay, so with that, let's jump right into some of the design principles. We wanted to build everything in Postgres, no questions asked. So all the Postgres isolation levels, the Postgres transactional semantics, all of the advanced features and extensions, and the ability to do rolling upgrades and downgrades across major Postgres versions. That last one was really hard. It's not something that, as far as I know, anyone else really does. And it's something that, we're pretty proud of having implemented. It took a lot of work to really, to bring it to fruition. Anyway, so these are some of the Postgres features that we support, like on the right, like all the way to stored procedures and triggers and everything, right? So we pretty much, our goal is to support everything. We also go beyond Postgres. We address some of its architectural limitations. There are architectural limitations when it comes to the core database features, when it comes to scalability, your resilience, availability, DR, disaster recovery, and multi-region deployments, and security. So these are some of the areas that we go ahead and look at in more detail as it relates to modern applications, right? And the same thing when you look at it, when you flip the coin and look at it, like things like connection pooling and observability and perf tuning, when folks come from other systems or build services today like Lambda systems, they expect a lot of these things, right? So these are the things we're putting into Postgres at an architectural level. So, and I'm breezing through this section because we can get to the really, you need to know the layout of what we're building in order to talk about some of the details, right? The other piece that we did, and this was a foundational thesis, as a way of a quick background, I used to work at Meta before. And at Meta, what we learned and what we felt was building cloud native applications is not about SQL and NoSQL. It's about relaxing constraints and deriving value by going faster in certain types of scenarios. So it's not SQL or NoSQL. It is about how can you operationalize and get those workloads that are being built to really run well in the cloud or in cloud native infrastructure, right? So to that effect, we started with 2 APIs on top because everybody we spoke to said, don't build another goddamn database. So when you really looked into it, we figured out what they meant to say was, don't build a new API. No one understands what a new API will do. However, existing databases like Postgres, like say Oracle, Mongo, all of these things, you have an intuition as to when to pick them. And so that's how the industry operates. So, we started out with 2. One was Apache Cassandra based, and the other is obviously Postgres. And now the DocumentDB folks at Azure are building a Mongo API on top of Postgres. So this is something we inherit, and we can obviously, being a scalable and resilient version of Postgres, that's pretty exciting. There's Oracle as well that we're working with some folks on, and the industry in general is building more and more of these emulation layers. Presumably because GenAI is making it faster to go in that direction, right? So this is something that we're just seeing as a trend. Okay, so let's take a look at the architecture at a glance. At the highest level, we wanted to achieve Postgres functionality, right? So the way we did this was we took the left and moved it to the right. Left is a very, very high level view of what Postgres is. Think of the query processing engine of Postgres as the green box and the storage components as the blue box below. So we retained the green box, right, and made it stateless and to be able to run on any node. and replace the blue box with our own storage layer, which is a distributed transactional storage layer, right? So that means you're now the blue box now is distributed and replicated, and it gives the information to the green boxes above in the way that Postgres expects it as a tuple. So green box just does its thing and fires off queries. The storage layer does its all of the filtering, fetching, all of that stuff, and presents the data in the way the green boxes would have had them in the left, right? Like the Postgres query processing engine. Obviously, if you do this, you get into it works, but the problem is it doesn't work very well from a performance standpoint because you're now reading all the data up to a single node and then doing a bunch of processing there. So that doesn't work really well. So the next step immediately that comes up is to start doing these push nodes. How can you push more and more operations to where the data is? How can you be smarter about how little data you can transfer between these nodes, right? That becomes the name of the game. And so that's something that we focused on quite a bit. And I'd say all of these things are still going on because Postgres is improving and we're still bringing more of the Postgres features into Yugabyte. So these are all like a continuum, right? This is the way it continues to work. And another aspect that we look at is how can we match the performance of Postgres? And this is where it gets into really interesting stuff. YugabyteDB is a log structured storage engine, and Postgres uses a B tree format to write into disk. I hope folks are familiar. If not, maybe ask Andy, he'll tell you in a different class. But log structured is really good for SSDs, and it has a lot of good properties. However, the Postgres cost-based optimizer and its performance is tied at the hip to the way it stores data on disk, right? So this is something that we've been looking at, and this is almost a 2-year journey for us where think of this as the different access patterns that Postgres exposes, and we started out at a pretty low number, and we're working our way to a pretty high number, right? In terms of what we're able to support, the number of comparable operations we're able to support with respect to Postgres, as well as the cost-based optimizer. In this case, Postgres works on a single node, so the way it sets up a query plan and the way it executes any simple query that any query that a user does is often optimized for a single node. And we are a distributed database, which goes after a distributed plan. However, a lot of our users complain that, look, this was a simple query that was just a couple of gigabytes on Postgres. It would run on my laptop. It doesn't really work. It's like 100 times worse on Yugabyte. Well, the problem is we sharded it and moved it all over the different nodes. And if you're fetching 1,000 rows and you're returning one, fetching 1,000 rows from local disk, your order of access is in the microseconds. So 1,000 rows would be in the order of milliseconds, and you filter it down to one row and you return it. Great. Fetching 1,000 rows over the network is in the order of milliseconds. So that would be in the order of hundreds of milliseconds to a second. So your performance sucks, but no use telling the user that because they're thinking it's just 1,000 rows. How bad can it be, right? So we had to do an adaptive thing where we're able to match Postgres at the lower, ends of scale when scale isn't big, while providing resilience, but be able to adapt to how to automatically shard and scale, right? And we had to build a whole framework for it to estimate what percentage of the time we picked the best plan versus Postgres. And we use the Taco framework. Like there's a academic paper on it. We use that paper to build a framework to then go test it. And so this is one of the parts of our testing suite. Okay. Postgres is a single node, and if you put 2 nodes of Postgres, people will tell you, why don't you deploy PG bounds? So simple, right?
Karthik, we're kind of short on time. You have like a last slide or something you want to show?
Yeah. So I wanted to say connection manager, building it in, sharding vector indexes and attaching it to the data. These are some of the topics that we work on. Looking forward, we're looking at a whole bunch of future things like putting in BM25, other types of indexes, so on and so forth, a whole bunch of stuff. I had something interesting that maybe if you had 5 minutes, Andy, I'll share. If not, it's okay. It was about a few interesting architectural war stories. I just have 3-4 of them, but if it's interesting, I'll show it. Otherwise, I'll skip.
I mean, it's interesting to me. It's just like we're out of time to get the students have other classes they got to run to. So
Got it. Okay, no worries. We'll do that another time. Yeah.
Any questions for Karthik? And again, we posted on Piazza for their interest and things like that. They're 2 of my best students, master student, undergrad, are currently at Yugabyte. I had some of my best students do internships there, and they've all been very happy. Okay? All right, let's give Karthik a round of applause. Thank you, man. Thank you so much for being here. All right. Have a good weekend. Remember, homework 2 is due on Sunday.
Cash money, click, flips, acrobats over tracks. 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 Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain. Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain.